A harvester moves across the cornfield like a conveyor claw, slicing through time. Behind it, trailers follow in silent synchrony, receiving grain as if in an industrial ballet. Nothing stops, nothing clogs. Everything flows, but this isn't improvisation. This is choreography, and its inspiration comes from a place far from the world of agriculture. The crushing pits of open-cast mining. In large mining operations, conveyor systems are designed for uninterrupted extraction. Rocks and ore flow continuously through calibrated belts, rollers, and feeders that never pause. The objective is simple: move mass efficiently, without loss, surge, or delay. In corn logistics, the same principle applies. But the cargo is lighter, more fragile, and alive in a different way. Here, machines don't just move material, they protect it. Flow matters, but so does form. At the heart of this operation lies the corn head, the front interface of the harvester. Its job seems simple: pull stalks, extract cobs, feed them into the system, but beneath its metallic surface is a carefully balanced mechanism of augers and intake chains, calibrated down to millimeters. Each component works to preserve what technicians call grain density uniformity, a rarely discussed but essential concept. If grain density fluctuates, the downstream flow destabilizes. The result? Internal traffic jams, grain shocks, kernel fractures, and ultimately economic loss. Inside this metal ecosystem, flow sensors and conveyor belts act like digital veins. They measure, adjust, and synchronize to ensure the grain moves at a constant velocity, preserving its structure. It's not just about speed, it's about integrity. The entire line has to breathe together. And this is where mining taught agriculture an unexpected lesson. In mining, haul trucks aren't just loaded. They're loaded according to patterns that minimize stress, distribute weight, and avoid compaction. The same logic now applies to modern grain trailers. Their internal geometry, the angles, slopes, and grain deflectors, are modeled after those load patterns. It's not about filling up as fast as possible. It's about how that load behaves inside the container, especially when it hits a bump or takes a curve. Precision matters. A 3% deviation in the alignment between the harvester's conveyor and the grain cart intake, just a few centimeters off, is enough to increase kernel fracture rate by 15%. That damage isn't visible at first, but in the drying system, those fractures cause uneven dehydration, leading to spoilage, shrinkage, or reclassification of the grain. In a market where margin is measured in decimals, that's a silent loss. That's why this system doesn't tolerate improvisation. Every auger rotation, every grain deflector angle, every slope inside a trailer, all of it is calibrated with one goal: continuous, damage-free flow. Corn doesn't just pour from one machine to the next. It's guided, like mineral slurry through pipes. It's channeled, like energy through a circuit. Because if it isn't, it turns to waste. Slowly, invisibly, but inevitably. What we're witnessing is not brute force harvesting. It's steel synchronization, a harvest rhythm borrowed from the deep logic of heavy industry. An operation that stretches across hectares but functions like a mechanical watch. Quiet, precise, relentless. And this is only the beginning. Because for every kernel that leaves the field intact, a complex system of sensors, angles, and calibrated logistics has already done its job, silently, faithfully, and with the exactitude of a mining operation, repurposed for grain. It begins with a misalignment, slight, often unnoticed, yet deeply consequential. The harvester discharges a river of kernels. But if the grain cart's intake is off by just a few degrees, the impact zone shifts. The result is not dramatic. There's no crash, no loud alarm. But inside that subtle mistiming lies a constant mechanical injury: fractured kernels. Each cracked grain is invisible in the moment, but its damage accumulates. In bulk transport systems, the notion of perfect contact between discharge and intake is a kind of mechanical ideal, always pursued, rarely achieved. And in that narrow gap, Where falling grain meets steel, energy disperses. If not absorbed correctly, that energy breaks what should remain whole. That's why some of today's grain carts now come equipped with real-time impact sensors installed precisely in their intake chutes. These devices don't just track volume, they measure the kinetic energy per bushel, second by second. Each spike in energy data represents a collision, a micro-trauma, between the grain and the surface it hits. Engineers now use that data not only to refine loading speeds, but to adjust harvester angles in real time, reducing internal abrasion as the corn travels from field to silo. What surprised many was that not all modern systems performed better. On several farms in the Midwest, older grain carts, equipped with slower but softer conveyors, outperformed newer high-capacity loaders when it came to kernel integrity. The difference? One design emphasized flow rate, the other impact absorption, and the results were measurable in quality reports. Less dust, fewer cracked kernels, higher classification grade. One Iowa operation took the principle further. Borrowing from fruit harvesting systems, where apples are treated with extreme care to avoid bruising, they added dampening foam pads to the grain cart necks. Simple, robust, and mechanically passive, these foam panels acted like shock absorbers, softening the grain's entry into the bin. The outcome was immediate. Fracture incidents dropped by nearly a quarter. The entire system required no digital control, no software, just intelligent design inspired by biological cargo. And that's the key insight. In modern corn logistics, quality is not just defined by genetics, moisture, or yield. It's defined by what happens between machines, in the airspace of the transfer. That transition from harvester to cart, from cart to trailer, must be engineered with as much care as the machines themselves. Because damage doesn't come from distance, it comes from contact. Behind every pristine corn kernel, there's a moment of impact that was either absorbed or ignored. That moment determines whether the harvest feeds or fails. Not every loss is visible, not every failure is loud, but every crack tells a story. And in precision farming, each one counts. Transporting corn, then, is not just about moving a product. It's about preserving its integrity under motion. It's a balance between flow velocity and mechanical cushioning, a system where speed, angle, and softness converge. Because every cracked kernel is a logistics error translated into biology. Not a harvest artifact, but a flaw in design. A silent reminder that the margin of success in agriculture often lies in the transfer zones. Those few seconds when everything must align. A loaded trailer may look complete, but what matters is how that weight is distributed. In corn logistics, tonnage alone does not define performance. It's the geometry of the load, the tension across the axles, and the relationship between mass and terrain that determine efficiency. And when this balance fails, the system pays in fuel, friction, and frame fatigue. It starts at the axle. Every trailer has a structural limit, not just in total weight, but in how that weight is spread. When corn is dumped unevenly, especially in haste during high harvest pressure, that imbalance generates torque, stress. Floors begin to bend. Beams deform microscopically with each bump in the field or curve on the road. Over time, that deformation accumulates. In a recent Embrapa audit, over 40% of Brazilian grain trailers showed signs of permanent floor distortion due to improper axle load distribution. These weren't accidents. They were the result of routine negligence made systemic. The engineering response has been digital. Some fleets now employ axle pressure sensors directly linked to the tractor's dashboard. These sensors generate live feedback, indicating precisely when and where to adjust the dump point. It's not a question of how full, but how aligned. In this model, every load becomes a calculated structure, not a hurried pile. But numbers reveal a paradox. On undulating terrain, trailers that were slightly underfilled, but poorly balanced, consumed 11% more fuel than those that were fuller but evenly distributed. The reason lies in the center of mass. When it shifts with every incline and descent, the tractor must compensate. That means more throttle, more correction, more energy spent controlling a mobile imbalance. Efficiency isn't about hauling less. It's about hauling smarter. One agricultural cooperative in Paraná changed its entire fill sequence during the 2022 harvest. Instead of loading from bottom to top, they began filling from the rear toward the front. This reversed approach stabilized the weight curve across the trailer's chassis. The result? A 17% reduction in average fuel costs across the fleet. No new machinery, no new software, just a deeper understanding of mass and motion. Because in agro-logistics, fuel is not only spent in kilometers, it's spent in the details of operation. A liter of diesel can vanish not in the open road, but in the moment corn hits the wrong end of the trailer. And when multiplied across thousands of loads and hectares, that decision becomes structural. Transporting corn, then, is not about how many tons are moved, but how those tons behave in motion. Behind every efficient trailer is a geometry of intent, a balance between physics and agriculture. And every load that flows correctly, every axle that carries evenly, tells a story of logistics done with precision. In modern agriculture, movement is design, fuel is consequence, and inefficiency, more often than not, is invisible until it becomes a pattern too expensive to ignore. Check the pinned comment. It's built for those who value precision. From a distance, the harvest seems complete when the combine shuts down and the grain leaves the field. But that is only one movement in a much larger operation. In truth, the harvest marks the beginning of a second, invisible process. One that unfolds in motion, governed by machinery, data, and engineering logic. It is here, in this delicate and powerful choreography of transport, that corn transitions from biological yield to mechanical responsibility. Transporting corn is not about moving product from field to silo. It's about maintaining integrity under pressure. A truck doesn't merely carry weight. It manages energy, distribution, vibration, slope, and time. Each of these variables has a mechanical signature, and when one falls out of rhythm, the system pays. In fuel, in breakage, in wear. That's why logistics in agriculture is not about scale alone. It's about synchronization. It's about the tempo of operations across space. Viewed from above, a harvest convoy resembles a living mechanism. The harvester, like a piston, draws in material. The grain cart functions as an intermediary chamber, cycling between supply and extraction. The trailer, the final carrier, acts as the artery that pushes the flow forward. But none of these elements act independently. They must time their actions with precision. Deceleration during incline, speed modulation during transfer, load balancing across terrain. This isn't simply mechanization. It's performance, rehearsed, refined, and now increasingly orchestrated by algorithms. The mechanical principles behind this choreography are borrowed from fields far beyond farming. Torque modulation from automotive engineering, load distribution from civil construction, flow regulation from fluid dynamics. In the case of corn, even the angle at which it falls into a bin must be considered. Too steep, and it fractures. Too shallow, and it stalls. Sensors now monitor vibration and grain temperature during transport, transmitting data that guides real-time adjustments. These are not luxury features. They are necessary tools for preserving value. A remarkable example of this precision engineering comes from a logistics project in central Argentina. Using predictive models and artificial intelligence, the operation aligned harvester offloading, cart approach, and trailer dispatch in a fully integrated system. Instead of waiting for the cart to arrive, the harvester received a time-coded signal telling it when to slow down, based on the current position and load status of the approaching vehicle. Similarly, trucks received optimal idle sequences to avoid overlap or delay. The effect was immediate. Idle time dropped by 28% over one harvest cycle. But more importantly, kernel quality remained consistently higher, and fuel consumptions decreased despite no change in route or terrain. This is the future of agro-logistics. Not faster, but smarter. Machines no longer just respond to commands. They anticipate, synchronize, and self-optimize. What results is not automation in the traditional sense, but conducted movement, where each element behaves like an instrument within a larger composition, and the more precise the choreography, the more efficient the outcome. Corn in this light is more than a crop. It's a signal, a visible expression of an invisible system performing at its peak. A kernel that reaches its destination intact is a sign that the entire chain, from soil to silo, operated in harmony, not by chance, not by brute force, but by mechanical intelligence shaped by human design. Agriculture today is no longer just a relationship with the land. It is a partnership with machines, with data, and with precision systems that extend far beyond the field. Behind every grain that arrives unbroken lies a choreography of weight, force, time, and intention. And in that choreography, we glimpse a future where feeding the world means conducting the invisible, with clarity, coordination, and the quiet mastery of engineering applied to motion. Curious minds notice details. Don't skip the pinned comment today.